So today we will discuss about potential energy and potential function. Yeah. So in the last week I think. Last week we have discussed about a quantity called electric field. Yeah. For example, if we consider a point charge, yeah, capital Q, this is a charge source charge, yeah. Okay, so this E here equal to Q over 4 pi epsilon 0 R squared, and there is also R hat. Okay, R hat is a unit vector. Yeah, we have discussed also yesterday, last week. Yeah. And for example, if we consider the magnitude of potential, we have only capital Q over 4 pi epsilon 0 R squared. Okay, so in this case, this E, okay, we could express it in terms of a function, a function. So this is basically a function. Okay, so this function we call it scalar potential. Scalar potential. This is, we call it scalar potential. So what it means, well, if you want let's say electric, complete name, electric scalar potential. Oh. Okay, so in this case, we have a potential functional. Oh yes, this scalar potential can be introduced, yeah, if E doesn't depend on time. Okay, so basically this is static. Okay, and in this case we call it electrostatic case. Okay, because the potential doesn't depend on time. Okay, any question about this aspect? Any question or comment? Oh yes, I have uploaded this whiteboard for last 2 weeks, yeah, in EduNext. Yeah. I think in module 2, I think you could also see. You can also download. Yeah. I hope you could read the file. Anyone already download the file in EduNext in module 2? Anyone? Hello? Anyone already download?
I am trying to download it, sir.
Okay. Good. Just a moment, yeah. Jeffrey. Okay, Aryoga. Okay. Okay. All of you could see, I mean, you could read, yeah, all of you. You could read clearly. about the whiteboard, the file is not corrupted or okay, is there any problem with the file?
For me, it's clear, sir.
Okay. Is there anyone have a problem? If you could raise your hand. Anyone have a problem with the file? Just a moment. Okay, I think it's not a problem. Yeah, yeah, it's high definition of well, not SVG, I think, the file type of the file. So you could, I think, read it clearly. Okay. Okay. So this is an example, yeah, for a function, a scalar function called scalar potential. Okay. So the potential of a scalar function called potential, electric potential, is introduced by using energy work theorem. So if we consider, for example, any source charge, okay, any source charge here, for example, this is a charge Q here, capital Q, and this is a test charge Q here, and we have we call it, this is, oh, sorry, oh, okay, this is R, okay. So this source charge Q is trying to move this test charge for at this new position. For example, this is R1, for example, and we call this is new position. We call it R2. Okay, so somehow, or we call it not R2, maybe RF, final, and this is RI. Okay, initial. Initial is awal, F final. Okay, so this capital Q here is trying to move this test charge Q, for example, from point A to point B. Okay. So because the force that acts on the test charge Q is equal to F equals to Q times E, where E is the electric charge from the source of the source charge. Okay, capital Q. Okay. So using work energy theorem, energy work theorem, so the work of okay. Okay, so this is the work. Okay, so W equals to integral F. This is the force and dot ds, yeah, vector. So we call this is displacement. Yeah. This is displacement. Okay, so if we plug in this F, yeah, to this star, this equation, then we will get the work that moves this test charge, yeah, from A to B is equal to Q times minus delta V. Okay, so this is called energy potential, this W, yeah, capital W. Okay, and this delta V here is potential function, or potential functional we call it. Okay, is there any question regarding this material? Anyone? Comments? Anyone? No. Okay. Let us continue. So if we consider the point charge particle as the source, okay, using this definition, okay, this delta V here, okay, so delta V equals to minus integral Ri to Rf E dot dr, okay. So in this case, okay, for example, we get for point charge particle, we get this minus delta V is minus Q, the difference between capital Q over 4 pi epsilon 0 Rf minus capital Q over 4 pi epsilon 0 Ri. Okay. So from this example, we can conclude, yeah, this is a deduction, yeah. So we can conclude that this delta V here is equal to minus integral Ri to Rf E vector dot dr vector. Okay. As the result, this should be equal. Delta means that VRF its final position minus VRI, where Ri is initial position. Okay, so commonly Ri we could state that this is the point of reference. So the point of reference, it means that we could set, for example, in this example, in point charge particle, this VRI goes to 0, okay, where Ri is at infinity. Okay. Okay, is there any? Okay, I will. Okay, so let us continue. So there is a capital U, we call it energy potential, equals to Q, which is the test charge, and then V, which is the energy function, or sorry, potential functional of source charge. Okay, this capital V. Okay, so delta U also equals to U Rf minus U Ri. Okay, equals to Q delta V. Okay, so Q is a constant. So if the energy potential changes, then the scalar function must also change. Okay. So okay, this is an example for a point charge particle. Okay. So for example, if we have Just a moment, just a moment. Okay. If, for example, we could also state that, so this is the difference of potential, okay, delta V. Okay, we could also take that this V here, I'm sorry, like 1, 2, V, just a moment. VR, okay, this is minus integral E VR plus C, okay. So if the integral have a boundary, yeah, Ri or Rf, so this is the integral without, well, you could also set that, just a moment, integral tak tentu ya, in English, ya istilahnya kalau yang Ri, Rf itu integral tertentu, kalau ini integral tak tentu. Oh, indefinite, indefinite, I forgot the English. So this is indefinite integral, and this is definite integral. So we have boundary here. Okay, for definite, so indefinite integral, we get this one. Okay, this is equal. Okay, so this is equal to this one. So this is a constant, yes. And this constant also, we call it, yeah, the points of reference. Okay, so it depends on the choice. For example, if we take this R to the infinity, we have V at infinity. Yeah, if you plug in this R to infinity, we will get this Q over 4 pi epsilon 0 R. So if R, we take the limit to infinity, so it should be the first term here on the right-hand side vanishes, okay, should vanish, okay. And then plus C, so this is equal C. So what do you want? Take the C, for example, we could also take that this C equals 0, okay. So if this is equal 0, so it means that if at the infinity we have the potential equals to 0, okay. So the form of the potential, we have this VR as a function of R equals to capital Q over 4 pi epsilon 0 R, okay. So this basically, this form is commonly used in the literature, for example. Yeah? If we take the points of reference at the infinity, at the asymptotic point, the asymptotic limit, sorry, we get this V at infinity equal to 0. Okay. Any question about it? Okay. So, for example, if at the infinity, we could also set that C is non-zero. Yeah. So we get that this VR is equal to this one, okay, where C is the value of the potential at the infinity. Okay. Any question about it? Any question? Any question? No. Okay.
Recording in progress.
Okay, any question? Any question? No. Okay, this is example for a thin shell, a charged thin sphere. Oke, jadi hanya kulitnya saja, bola berkulit. Okay, as we have discussed last week. Okay, we have region 2 and region 1. Yeah. Region 1 is inside the sphere, and region 2 is outside the sphere. Okay, so E2 in this case is capital Q over 4 pi epsilon 0 R squared. So R is greater than or equal capital R. So if we use the above formula, we get that this V, yeah, at the second region, at outer region, okay, outside the sphere. So this V2 is equal to Q over 4 pi epsilon 0 R plus C, okay? So C we determine, for example, if we take V to infinity, this V2 to infinity equals 0, so it should be C equals 0, okay? Okay, is there any question? Any question? So for C equals 0, okay? Sorry. So for C equals 0, this V2 R, yeah, if capital R, if we evaluate this V2, evaluate at R equals capital R, which is on the skin, yeah, on the surface of the sphere, okay? So we get that this equals to this one, okay? If this is C equals to 0, okay? So this V2 R here equals to Q over 4 pi epsilon 0 R, okay? Plus 0, of course. This should be plus 0, sorry. Okay, any question? So this is the first case. The second case, yeah, for example, if we want, if we take this V2 at infinity is minus, for example, yeah, minus Q over 4 pi epsilon 0 capital R. Okay, so this is also a constant, which is non-zero. Okay, so this V2 as a function of R, okay, is equals to Q over 4 pi epsilon 0 R minus Q over 4 pi epsilon 0 capital R. Okay. Is that clear or something you want to ask? Or any question? Any comment? This is the second example. The first example, C, the constant equals 0. The second example, C equals 2 minus capital Q over 4 pi epsilon 0 capital R. Okay. So the potential change, yeah, the potential is changed, yeah, by only a constant, but the different constant, which is non-zero. Okay. So if you evaluate this capital R, sorry, this R equals to capital R, this second form of the function of the potential, you will get the potential at on the surface, on the sphere surface, will be 0. Okay, will be 0 if you evaluate this R equals to capital R. Okay. Is there any question? Any question? No question. Okay. So in this case, this is not the third. Yeah. This is not the third. So in this case, yeah, this V2, if we evaluate this R equals to capital R, yeah, on the surface, the sphere surface, okay. So you will get this V2 equals 0. Okay. No question, no question. Any question? Or no question? Okay. Okay, so this is the unit, yeah. The unit of E, the electric field, is Newton over Coulomb. But the unit of potential, yeah, potential is Newton meter per Coulomb or Joule per Coulomb. So energy potential is Joule, yeah, in this case. Any question? Any question? No. Okay. So we will, okay, let's. Okay. Okay, have you seen, do you see the picture? Oh, hello?
Yes, sir.
Yes, sir.
Hello, anyone? Do you see the picture? Hello?
Yes, sir. We
Yes,
can see the
sir.
picture.
Okay, so, okay, this is the, from the book. So we have discussed also about this electric potential. Yes. This is, we have discussed this, the difference of energy potential. Yeah. This equation 25.1. Yeah. So this source charge is trying to move this test charge from point A to point B. Okay. Is there any picture here? No. So using this formula, this relation between energy, the potential energy and the potential functional is V is the potential functional, U, capital U, is energy potential, electric potential, electric energy function, okay? This U here. Okay, so from this formula, we get that the potential difference, yeah, VA, VB of minus VA. So potential difference delta means final minus initial, okay? So in this case, we have minus VB minus VA, okay? In this case. Okay, this is the unit. We also have a unit, we call it electron volt. So electron volt means that the energy charge field system gains or loses when the charge of a magnitude E, that is an electron or proton, is moved through a potential difference of 1 volt. Okay, so this 1 electron volt is equal to 1.60 times 10 to the minus 19 joule. Okay, but in this this unit, electron volt, we will use it often in the last chapter, I think, in modern physics. Yeah. In this case, it's really well. We're not use this one. It's not common, yeah, in like an electrostatic or magnetostatic or electron volt unit. Okay. Any question? So this is the example for where a proton is released from the rest in the uniform electric field that has magnitude 8 times 10 to the 4 volt per meter. Okay. This is the electric field. The proton undergoes a displacement of 0.5 meter in the direction of E. Okay. Find the charge in the electric potential between A and B. Oh, sorry, find the change. Sorry, find the change in electric potential between point A and B. So point A here, B here, yeah. So this D here equals to 0.5 meter. Okay, it's very, okay. Okay, so delta V, yeah, the difference of the potential difference minus equals to minus E times D, okay? So this should be minus 8 times 10 to the 4 times 0.5. So we will have, this should be delta V, this minus 4 times 10 to the 4 volt. Okay. So the question is, why this is minus? Any comment? Hello? Any comment? Any comment? Why the sign is minus here? Any comment?
Probably the direction of the path it's moving, sir.
Sorry, yeah. Can you repeat?
I think it's the direction of the charge particle moving.
Vertical or horizontal moving?
I mean the direction the proton moves.
Yes.
It's going to the negative.
Okay.
So that's why the sign is also negative.
Okay, yeah, thank you. Okay, so this positive charge move towards negative pole, okay? This negative pole, okay, the potential here, yeah, in the negative pole is clearly less than the potential in at the positive pole, okay? So the difference should be less than 0, okay? Because the final potential is minus the potential which is positive, okay? So the difference should be negative. Okay, good. Thank you. Okay. B, for example, find the change energy potential. Okay, so you just times times it with E, yeah, the test charge. Okay, so this should be this delta U here. Okay, C, find the speed of proton after completing the displacement 0.5 in the electric field. Okay, so we have, because this electric potential is a constant, and also this electrostatic is also a conservative force, we have this delta K plus delta U equals 0. Okay. So delta K, yeah. So from the statement of the problem, so a proton is released, so should be its initial condition should be 0, okay, at rest, okay, the speed, okay, this little a half mv squared minus 0 plus E delta V, okay, so we will get that this V here equal to square root of minus 2E delta V over M. Okay, we will get that the speed of the proton after the displacement 0.5, the speed should be 2.8 times 10 to the 6 meter per second. Okay. Okay, what if, like Marvel, what if the situation is exactly as the same as the figure 25.6, but no proton is present? Could both parts A and B still be answered? Any one of you? Any comments? If the proton is not present, what happens? Hello, hello? So let's see. Rachel, Zaneta, Rachel, ini kenapa nih kok tidak nyambung ininya, audionya? Rachel, ini kenapa nggak nyambung audionya? Halo, Rachel, ini kenapa nggak nyambung audionya? Halo? Rachel, halo? Muhammad Zahid Farel. Ini Davin tolong dirubah ini namanya. Fadgam juga nih belum ini. Fadgam tolong dirubah, Davin tolong rubah. Atau saya put di waiting room nanti, nggak dihitung absen. Muhammad Zahid Farel. Karena kalau nggak ngejawab saya put di waiting room. Dan tidak di absen hari ini. Lilo Handaru. Lilo Handaru. Yeah. What is your question? For what if the proton is not present? What happens?
There will be no
No what? Hello?
No
Hello?
electric charge.
Amadea. Amadea
Yes.
Nora Liza. Yeah, what is your answer? Hello? Hello? Amadea?
Is it no acceleration?
No acceleration. Wildan Akmal. Wildan Akmal.
Yes, sir.
Yes, what is your answer?
I think there will be no charge, sir.
Of course, not charge. And then what about this delta V or delta K, delta U, something like that?
I think I'm agree with Dea. There will be no acceleration.
Sorry?
Yes, I think I'm agree with Dea. There will be no acceleration.
No acceleration. Okay. Sanwirya Mulyo.
Yes, sir.
Yeah, what is your answer?
For me, I think the potential energy of this system is going to be zero. So
Yeah. Okay, thank you. So if the potential, sorry, if the electric charge or proton is not present, so this delta V is equal to 0. Okay, delta U also equals 0. Okay, and also this delta K equals 0. So everything is 0 here. Okay, so everything is trivial. Okay, so this is the example. Yeah. If, for example, we have a source charge Q is trying to move a test charge from A to B. Okay, so this is basically the potential difference here. VB minus VA. Okay. Okay, any question? Okay, let us continue. So this is okay. So this is the the picture here. If we consider this 25.11, where R is the square root of x squared plus y squared. Okay. So it looks like a cone. Okay. Okay. This is the electric potential for two charges. Okay, two charges. Two charges. Okay, this is the example. The electric potential due to 2-point charges. So we have Q1 equals to 2 microcoulomb. Okay. Is located at the origin, and the charge Q2 is minus 6 microcoulomb, is located at 0.3 meter. Shown in the figure. Okay, this one. Okay, this is A here. So question A, find the total electric potential due to these charges at the point P, whose coordinates are 4, 0. Okay. So for two charges, we get this VP here. Okay. So we have two charges is QE times Q1 over R1 plus QE times Q2 over R2. Okay. So you should see this one. Okay. Okay, any question? Any question? Okay, B, find the change in potential energy of the system of two charges plus a charge 3, Q3 equals to 3 microcoulomb, okay? So it should be that we have this VP here, okay? We have minus 6.29 times 10 to the 3 volt, okay? If we take, if we include the test charge, okay, so it should be the potential energy, the change in the potential energy. Okay, so it should be, we just take delta U over Q3 times delta V, okay? So delta V here is the minus 6.29 times 10 to the 3, okay, and the test charge is 3 times 10 to the minus 6 coulomb. Okay. So we will get that the energy potential, the difference, the energy potential difference should be minus 1.89 times 10 to the minus 2 joule. Okay. Any question regarding this one? Any question? Hello, any question? No. Okay. If you are walking through this example, what if here? So wait, with the classmate NC says, wait a minute, in part B, we ignore the potential energy associated with the pair of Q1 and Q2. How would you respond? Any question? No. So, so given the statement of the problem, it is not necessary to include this potential energy because part B asks for the change of the potential, okay? So this B is the potential change, okay? So this is not the, this is only the potential energy, not the change, okay? So the potential energy for 3 charge system, just like this one, this R12, R13 plus Q1, Q2 over R12 plus Q3, Q1, Q3 over R13 plus Q2, Q3 over R23. Okay, so this is basically the potential, yeah. This should be minus 5.48 times 10 to the minus 2 joule. Okay, any question? Any question? Any question?
Excuse me, sir.
Yes? Yes,
What
hello?
does being brought in from infinity mean exactly?
Yeah. Infinity is a place where it's far away, far away. Yeah, infinity means, just a minute. So R to plus infinity, it means far away. Far away. For example, for atom H, ya, atom like hydrogen, atomic like hydrogen, atom H. So we have only a proton at the nucleus, and also this radius, we call it Bohr radius A0. If the atom, if the electron, yeah, at the ground state, at the ground state, so this R here is equal to Bohr radius. Bohr radius is around 10 to the minus 10, I think, meter. Okay, so we could also, for example, consider, for example, the influence of the proton, for example, for R, for 1 meter. Okay, 1 meter. 1 meter compared to Bohr radius, which is 10 to the order of the Bohr radius minus 10. Okay, this is 1. Okay, so we could also say that this R equals 1 meter is also infinity. That's the physical reason. Okay. Okay, I will summarize the lecture in Indonesia. Oke. Jadi pertanyaan Anda itu apa yang dimaksud dengan infinity? Infinity adalah tempat yang sangat-sangat jauh sekali. Oke. Jadi tempat yang sangat jauh itu seperti apa? Nah, kita perbandingannya begini. Kalau atom hidrogen misalkan, dia punya proton dengan elektron kan. Nah, jarak antar proton dengan elektron itu sekitar 1 A0, kita sebutnya 1 Bohr radius lah ya. Bohr radius A0. Jadi A0 itu ordernya 10⁻⁻10 meter. Oke. Nah, sekarang kalau saya meninjau misalkan pada jarak 1 meter ya, dari proton, 1 meter dari proton. Proton itu 10⁻⁻10 meter aja udah dibilang jauh, apalagi yang 1 meter. Jadi itu yang sangat-sangat jauh. Jadi R1 sama dengan 1 meter untuk level skala proton itu sudah sangat-sangat jauh gitu. Dibanding dengan yang ini, yang 10⁻10 ini yang dikatakan Bohr radius Bohr lagi. Jadi seperti itu. Mudah-mudahan tuh bisa menjawab. Ada pertanyaan lain nggak? Atau ada komentar lagi? Oke, ada yang lain lagi? Atau cukup jelas? Tadi yang nanya siapa?
Saya, Pak. Udah cukup jelas. Makasih, Pak.
Cukup jelas, oke ya, sama-sama. Terima kasih. Oke. Ada lagi yang lain? Pertanyaan? Oke. Oke, ada lagi yang lain nggak? Oke, jadi saya ulangi lagi ya dari awal terkait mana tadi? Terkait apa potensial skalar gitu ya. Oke. Jadi kalau misalkan saya ambil contoh muatan titik ya, Q besar, ya E-nya itu adalah bentuknya seperti ini yang dilihat gitu ya. Nah, E di sini itu bisa saya nyatakan sebagai turunan sebuah fungsi gitu ya. Nah, fungsi ini adalah fungsi skalar kita nyebutnya. Gitu ya. Jadi di sini ada tanda minus di situ supaya konsisten aja dengan E gitu ya. Jadi ini memperkenalkan kita bahwa medan listrik ini bisa dinyatakan sebagai turunan dari sebuah potensial. Tapi sekali lagi, hal seperti ini bisa terjadi ketika medan listriknya itu tidak bergantung pada waktu, hanya bergantung pada ruang. Nah, ini yang dikatakan apa namanya, yang di dalam kurung ini itu adalah Q apa namanya 4Pi epsilon 0 kali R. Jadi ada term yang disebut namanya fungsional, disebutnya potensial fungsional ya bahasa Inggris ya. Kalau bahasa Indonesia apa ya? Fungsi potensial kali ya. Gitu. Sebentar ya. Oke. Oke, kemudian dari sini kita memperkenalkan definisi fungsi potensial gitu ya, dengan menggunakan teorema usaha dan energi. Usaha dan energi itu kan udah Anda pelajari semester lalu. Ya. Jadi rumusnya itu adalah W, usaha itu adalah integral dari F dot ds. Oke, F itu adalah gaya atau disebut force, ya. Dan ds itu adalah displacement kita nyebutnya, perpindahan. Jadi kalau misalkan sebuah muatan sumber Q besar itu memindahkan muatan tes ya, Q kecil dari A ke B, itu maka nanti didapatkan W-nya usahanya itu adalah, jadi kalau apa namanya gaya pada muatan uji itu adalah Q kali E, di mana E di situ adalah medan listrik dari muatan sumber. Oke, sehingga nanti usahanya itu akan saya dapatkan seperti ini. Di mana delta V di sini itu adalah yang disebut namanya beda fungsi potensial atau beda potensial. Oke. Nah, ada pertanyaan nggak? Oke, nah sekarang kalau misalkan saya ambil, ini contohnya aja nih untuk misalkan partikel titik, gitu ya, itu bisa saya dapatkan bahwa potensial titik itu bentuknya itu tadi seper R gitu itunya, sebanding dengan seper R potensialnya. Jadi tepatnya itu seperti inilah kurang lebih. Jadi ini adalah ini. Sorry. Sorry. Oke ya, dapatnya ini adalah jadi V di sini itu sama dengan VR ya, sama dengan Q per 4Pi epsilon 0 R tambah C. Nah, C di sini itu kita nyebutnya itu adalah sebuah konstanta. Jadi konstanta ini diambil bergantung pada pilihan yang kita inikan. Jadi biasanya misalkan saya ambilnya R-nya menuju tahingga, V tahingganya itu 0. Ya. Jadi yang suku ininya akan 0, yang suku pertamanya. Tinggal C kan. Nah, C mau seperti apa? Kalau C-nya itu sambil 0, berarti V di tahingga 0, maka saya dapatkan VR ini adalah Q dibagi 4pi epsilon kali R. Gitu. Ya, jadi ini istilahnya bentuk potensial yang common, yang biasa dipakai di di statik lah gitu, intinya gitu. Ya. Aduh, kenapa sih ini? Oke. Nah, ini contoh lain misalkan untuk yang C-nya tak berhingga. Jadi kalau C-nya tak berhingga, ya berarti kalau R-nya menuju tak berhingga, berarti kan C di sini tidak lain adalah nilai potensial di V tak hingga, di R tak hingga. Gitu. Itu aja ininya. Nah, ini sambil contoh lagi misalkan untuk bola ya, tapi hanya kulitnya aja, jadi disebut thin sphere shell. Jadi dalamnya kosong, cuma kulitnya, jadi punya radius R besar gitu ya. Nah, daerah satunya itu yang lebih kecil dari R besar. Artinya di dalam bola, kalau di luar bola itu R lebih besar atau sama dengan R besar gitu ya. Nah, kalau untuk di luar bola itu kita dapatkan E2-nya seperti yang udah dibahas minggu lalu, itu adalah Q besar dibagi 4pi epsilon 0 R kuadrat. Oke. Sebentar dulu ya, saya